A warm welcome to another session, Data with Nick the Greek. And today we're gonna continue our discovery journey with how the algorithm of Spark works, how Spark is really calculating the number of partitions. And we're gonna deep dive a little bit into the actual algorithm today, because we realized our basic algorithm yesterday wasn't always very accurate. Yeah, and so just to repeat what we're actually doing it, so it's really important to understand how Spark creates the number of the partitions. And it's important to know about the performance, how we can influence it so that we can also improve the performance and debug better. And you already learned the number of partitions and especially empty partitions is relevant for your performance. So if you have like 5 partitions and have 4 cores, you basically have 1 core which is doing the job alone at the end, especially if you have uniform data. So that means also the distribution of the data is relevant. And that's what we're gonna deep dive into the next sessions. Also coalesce and especially partitioning, if you want to increase the number of partitions later on, is really cost expensive. And if you can already influence at the beginning, it's really a big win. So as always, we're gonna start with some setups, our Spark session. We have our generator to write the data. And of course, we have like a function where we can influence our 3 parameters, which are relevant: max partition bytes, open cost bytes, and min partition number. Max partition bytes is the one which we're mainly gonna be focusing for now. So just to repeat again what influenced the partitions. So we have the number of cores in the cluster, which is the minimum partition number config, which is so above, but we use a default parallelism value, which is the number of cores equaling 4. We have the file size and the number of Parquet files. We also have something called blocks or row groups in Parquet files. We will not talk about it today. We have then the max partition size, which basically is roughly said limiting the size of a partition. And we have the max cost per byte, which is roughly representing the cost of creating a new partition. We will technically take a look into the cost per bytes as well as part of the algorithm, which basically is adding a little bit more size, which is called padding. But the influence of it you're gonna really see if you are looking on smaller data sizes. So last time we have 2 experiments. One's 4 files, each 65 megabytes roughly, and then the second one 8 files. Just to have a look shortly on the 4 files one, but we're gonna be basically looking on the 8 files one. And just to repeat what we discovered last time. So we have here our set configs where we can influence the max partition bytes. And as we already see, 64.8 megabytes is 1 file. So if you're running it with max partitions bytes of 8, we expect that the actual number is 4. And also our basic algorithm is saying the same thing. The interesting part which we discover is if we're going a little bit lower. So let's say we're going 50. And what we see suddenly, we have 6 partitions. Of course, our algorithm estimated it's not too bad, but still it's somehow interesting to see how the number of partitions are actually calculated there. Interestingly, it's gonna become later on. So let's justify what's happening if you go even lower, because that's, I think, where the algorithm didn't work very accurate anymore. Yeah, so here you see it says 13, but actually it splitted it even more partitions. And the reason for that is actually the open costs, which we're gonna see in a bit. So doing a similar experiment on this side. So let's go with 65 max partition size again. with 8 files, and let's see if the algorithm is estimating correctly. So it's 8, but again, the same thing, even with the 3 ones, if you go down to 30, it's splitting into a lot of files, and here we already have also deviation. And another interesting part is also, let's see it here, or is it? So we can see that the size per core is 130 megabytes, meaning 2 files, as we have 4 cores, we have 8 files, 2 files are 129.7 megabyte big. And let's say we want to combine them into four partitions. So you would think 130 megabytes is enough to make 8 partitions out of it. So the algorithm has 4 partitions out of it. So the algorithm says 4, but actually it's still 8. And there's also the open cost involved, which influences this. So if I'm gonna add the 134, I think I'm not saying nonsense right now. Yeah, it's 4. Only then we are going down to the 4 partitions. So let's have a look step by step on the algorithm. Just to repeat shortly the algorithm which we developed in the previous episode. So we are getting our max partition bytes out of the Spark configuration, and we're getting the minimum partition number, which is our default value of 4. And so what we're doing is we just divide the size of the total of the whole file by the minimum number of partitions, which is the default parallelism. So that means that's how we're getting to 129.7, because our file size is 518. So divided by 4. And then what we're doing is we're checking if the max partition bytes is smaller than the size per core. So if it's smaller, we're basically limiting the number of partition. If it's the same, we just let the default parallelism split the files based off the number of cores. And that's something we can also see here. So the partition size is now the size per core. But if you're gonna go below this value, 129, you can see that the algorithm actually says that the partition size should be 129 and not 129.7 anymore. So now I said that the size per the open cost in bytes has some influence. And let's extend the algorithm just a little bit. So what we're doing is, first of all, we are getting our open cost in bytes. And what we're gonna be doing is we are gonna do this padding, which is basically adding per file 4 megabytes to the total file size. So basically that's how we end up with the file size padded. And now we already see that the number of files has an influence on how the partitioning is happening in the background on Spark. And the rest is actually the same thing. So instead of our size per core, we take we calculate the size, the padded size per core based on the padded file size. And then we have the same calculation for our partition size here. And the only difference we're gonna experience is in this area of plus 8 megabytes, where we now have the size core padded, as we have 2 files per core, which is 8 megabytes bigger. So we're gonna see that size per core padded gonna be the partition size just a little bit earlier. So let's activate this function, and we went with 129. So you can see here the 129, and here the 129 is the max partition size, which we're gonna see where the max is the case in a bit. So now let's go a little bit above 131. Now you see here where gets a little bit different. So we have now the max partition is still 131, but here it's like the size per core. And you see that the difference is here 8 megabytes higher. And that's why we have also different estimate. So basically what Spark is doing, I mentioned the max partition size, it does a different calculation of the partitions actually. So here we are still estimating the partitions. And let's go to a third step of the algorithm. So let's close this one. That's the algorithm which we have right now. The only difference which we're gonna be adding, but it's not really influenced right now. So I said the open Kostenbytes is only relevant for smaller files. We have a two-step calculation of the max partition size. So what we're adding is, we are just checking if the size per core padded is smaller than the open Kostenbytes, which is 4 megabytes. And obviously this can only happen if the files are really small. Otherwise the size per core padded can actually not become below 4 megabytes. So you see for our experiment which we did above, the outcome gonna be pretty much the same. So let's run it once again. So the advanced algorithm is 4.2, and here we have also 4.2, and also the max partition size and the size per core is pretty much the same. But what we can see is still we have here difference. So basically, even with the advanced algorithm now, the estimated partitions are still not calculated correctly. So what is Spark actually doing in the background to calculate the partitions? The most important thing is, let's just close it. It doesn't calculate like that the number of partitions, but it uses exactly this value to split the partitions based on a specific logic. So what we gonna do today first. So we are taking a function which is basically creating a list with the sizes of the files. So Spark normally creates like a file object. We're not doing this complexity now. I don't want to recode the whole Spark module from Scala. But basically, we saw here that we have the compressed bytes. And this we're gonna get as a list. And I think I have the code already uncommented here, so I will just execute it to get our files list. So basically just the compressed bytes as a list. So there we go. Let's have a look how this list is looking like. It basically looks like that. So now we don't want to work with megabytes. It's gonna be with bytes. It's gonna be too complicated to understand what the algorithm is doing. But basically, the first algorithm, what it's doing is it splits this list, which we have here, into smaller pieces. So basically, let's say we have a max partition of 17 megabytes. And what it's doing is it results into this list. So basically it also does a sorting. Let me just deactivate the sorting shortly. It basically looks into each file and generates, like, let's call it virtual file with this, like you would actually split the files. So let's have a look into 50. How often did you fit the 17 in? 70 plus 17 is 34. And then plus 16, this is the remaining one, is 50. The same thing with 73. We have 1, 2, 3, 4, 17. So 17 times 4 is, what do we say, 68. And then 5 is remaining. the same thing with the next one, 35, 771, and so on. And basically what I said is what the algorithm is just doing, it's basically sorting them by size. So you have like the 17 megabyte files, those are basically based on the max split bytes at the beginning, and then we have the other files. And then, this is unfortunately not everything. So now let's also have a look on how big the file is. So we have 16. And now we have to put it into another algorithm, which is actually generating the file partitions. So if you're curious, you can also have a look into the Scalar file from PySpark in the background, but that's basically how it's done. So we see here the open constant bytes as expected is influenced. So right now I just commented it to put it to 4 megabytes, as we do here a small test with megabytes. And we have here our test results too. And we have to set the same max partition bytes. And now you see, okay, it's actually only 15. And before we have 16. And basically it put one file together. And actually, based on this, based on this simulated splitting, you also see already why we have suddenly so many partitions, because this splitting happens only virtually. Actually, we already said the snappy files, they cannot be splitted, basically. And just to have a look roughly, a rough look into the algorithm. So what it does is we have the open cost bytes, it gets the max split bytes and the file size again. We have here a list of the partitions which are created. So basically I'm just listing, in my case, a dictionary with some information. We have the current files and we have the current size, which is always getting into one partition. So what I'm doing is I'm now iterating through each file. I'm checking if the current size plus the file size is bigger than split bytes. So if you start with 17, it isn't. So you're skipping it the first round. Then we are adding here in our current size list a file size plus open constant bytes. And then we append only the file size without the open constant bytes and do another loop. So now current size is 17, adding another, and the second 17 of course leads to bigger than max split bytes, so we cannot further add anything, and then we are doing a close partitioning. So, and if we have current files, this is the case, we are adding a partition element. So we get the current files, the length of the current files, and also the sum of the partitions, and that's what you see here. So we have the 17 in there, we have one number of file, and then we have a partition size of 17. So, and then we're iterating through, but at some point we're gonna end up here with a 5. So, so let's say we have the 16 here, plus the 5 is bigger than max split bytes, gonna be added, but then we're getting the 5 in here. So current size 5 plus open cost bytes is 9. Then we go another round, 9 plus the second 5 is 13, so we are not above 17. Now we are adding the max again, 5 plus 9 there, so the total value is then 18, and 18 plus whatever, so 1 in this case, is of course bigger than max split bytes. And that's how we are ending up here. And we can also do the experiment. You're gonna see if you're gonna lower the value now to, I know, let's not go below max split open constant bytes, but let's say we have this one here. We see, okay, we have a number of 47 Partitions, what did we set? 5. We are getting 47 partitions. Actually, it's even the same in this case. So as we deep dive into the algorithm, let's now see if this algorithm can actually resolve our issue. So we have to do one correction. We have to adjust, of course, to do the calculation with the correct bytes. And now let's execute what's happening. So this was our basic algorithm. This was the extended one. This was the estimated average. And that's basically what we're getting out of our formula. So yes, we made it. But let's see, first of all, on our edge cases, if it works. So let's start with 140. That's where we expect that we're gonna have 4 partitions in here. So you can see it's 4, we were successful. So then we saw that usually it starts deviating when we are crossing the size per core padded, but and stay between or actual average size without any padding. So basically, let's say 134, for instance. So also here we see that we had here with a basic algorithm and extended a little bit of deviation, but also here we have the 8 estimate correctly. Now let's go a little bit lower, 90, which is somewhere between the cost per bytes and the number of partitions, still 8. Now let's go below the average file size, which is, let's say, for instance, 60. So here we saw some deviations already. Here it says 9, here it says 10. Here actually also it says 10. Not too bad. But let's now go a little bit lower, 20. So 28. Actually, okay. It's also estimating there quite okay. I'm surprised how good this average already is working. Let's reduce the max partition size even more. So, okay. It's still okay. I'm surprised in this test. I guess I didn't play around with enough partitions. I'm surprised actually that this value is until now for those cases now also quite well. But at the end you see that the logic which we implemented is quite accurately. And let me do one last experiment if we now get it to get some deviation there. Okay, now we finally got it to screw up this algorithm, this average. So you can see here it calculates 111, but actually here the number of partitions is 104. This is our calculation. That's basically what the number of partitions of Spark is returning us. Okay, one last thing I just want to mention. We're gonna take a look into the Spark URL last time as well. So I just want to show one of the codes. in Scala to just see, okay, what they're actually doing. So let me see where it doesn't want to open. No. Okay. So that's where the partition file logic is calculated. So here's the split file code, for instance. So you see there has some kind of offset. Yeah, I could also like calculate a little bit different. Here's the block splitting, which we will not look yet. But basically what I want to say is they create like partition file object. And if you're still remembering in the Spark UI, what we saw is that we have small kilobyte files, but with 0 rows. And my assumption is, I'm not 100% sure, of course, that this is happening based on the object size, which has still some metadata in. And so what I also want to mention, like some of those things I even myself don't understand like 100%. I mean, it's first of all Scala. So partly also like based on playing around and testing, I kind of estimated the algorithm, how it's working. So there might be some more complexity in there, which I haven't discovered yet, but you saw that until now for every file size, the algorithm which we developed together today brought a quite well estimation. And this is going to be the basis for our next session. We're gonna evaluate a little bit more how now, for instance, the max partition bytes influences the outcome of the partitions, but also like based on a bigger data set, the performance outcome of it. And with that, as always, thanks a lot for watching. Subscribe my channel. As always, more videos similar to that gonna come, which might be really interesting and helpful for you. And of course, feel free to comment if you have any questions, if you have any comments of things which could be improved, etc. See you in the next episode.